So we were still in our discussion of equivalence relations, and here's the definition again. A relation twiddle on a set A is called an equivalence relation when it satisfies the reflexive property, symmetric property, and transitive property. And then we had three examples. We had the example P, the partition of a set A into subsets. Example M, equivalence relation on the integers modulo M or modulo N. That was an equivalence relation. And then example S, where we took the subsets of a finite set and we said that X is related to Y when their symmetric difference had even order. And then we defined these things called equivalence classes. So given an equivalence relation, twiddle, on a set A and X in A, define the equivalence class of X as this. It's bracket X. It's the set of all Y such that Y is related to X. Then we proved the following theorem, which is the main theorem about equivalence relations. Let twiddle be an equivalence relation on a set A, and let X and Y be elements of A. Then the equivalence class of X is not the same as the equivalence class of Y if and only if they're disjoint. Equivalently, you can negate both propositions. Equivalence class X is equal to equivalence class Y if and only if they're not disjoint. So two equivalence classes are either equal or disjoint, and never both. Or sorry, are either equal or they're disjoint. Of course, not both. So equivalence classes partition, and here's the proof of that. Equivalence classes partition the set A. So that partition equivalence relation, which example P was our first example, is actually every equivalence relation. They all do that. Given an equivalence relation twiddle on a set A, the equivalence classes partition A into disjoint subsets, which are the equivalence classes, where equivalence class of X is equal to the equivalence class of Y if and only if X and Y are in the same equivalence class. So then, we want to look at some examples of what this partitioning is, because that's an important aspect of these equivalence relations. So back to example M. So you have some positive integer n, usually at least 2. And we have an equivalence relation on Z called equivalence modulo n, which is defined by X is equivalent to Y mod n when X minus Y is a multiple of n. So these are the equivalence classes. The equivalence class of 0 is all the multiples of n. The equivalence class of 1 was all the multiples of n plus 1. The equivalence class of 2, multiples of n plus 2, all the way up to the equivalence class of n minus 1, which is multiples of n plus n minus 1. So, for example, for n equal to 4, the equivalent class of 0, it's all the multiples of 4, which is the same as the equivalence class of 4. Again, the things equivalent to 4 are the multiples of 4. But, 0 seems to be the right choice to represent that equivalence class rather than any other multiple of 4. And then you have equivalence class of 1, 2, and 3. What about when n is equal to 2? Well, you have the equivalence class of 0, which is going to be what? Well, it's all the multiples of 2. In other words, it's what? Well, the
All even numbers?
all even numbers. And the equivalence class of 1, it's the set of all 2k plus 1. This is
All odd numbers.
the set of all odd numbers. Right, so that's going to be, definitely something very important when you study math at higher levels, this, notion of equivalence modulo n. Essentially, when you look at the integers modulo n, all the basic rules of, not all of them, sorry, I mean a lot of the basic rules of arithmetic with just ordinary integers carries over into integers mod n. But you're going to see plenty of that later. I'm not going to talk about it now. And then there was that last example, back to example S, symmetric difference. All right, given a finite set A, define twiddle on the power set of A, not on A itself, by x is equivalent to y when the order of x symmetric difference y is even. And we showed this is an equivalence relation. We showed that this was an equivalence relation. What are the equivalence classes? It's not immediately obvious, what it is. But, in order to find out, let's take a look at the symmetric difference again. So remember, the few facts. We haven't actually proved these ones yet that I'm going to list to you right now, but we will, and they're very simple, and I'm sure you probably know them already. Even plus even is even, right? 2 even plus odd is odd, and odd plus odd is what? Take two odd integers and add them, you get what?
Even.
Even. Yeah. And not just plus, but plus or minus. Okay. And then remember also the following. Right. A symmetric difference B, or X symmetric difference Y, is equal to, well, there was two ways to look at it, right? There was X minus Y union Y minus X, which was equal to x union y minus x intersect y. So when you look at it on a Venn diagram, right, here's set x, and here's set y. Here is x minus y, and here is y minus x. All right, and right here in the middle is x intersect y. And those three sets are what? So let's look at it this way. Forget about this one. These three sets are what? What was the deal with those three sets that was special? X minus.
Disjoint.
They're disjoint, right? Okay, so the order of x minus y is equal to what? Well, it's the order of x. Don't say minus the order of y. It's the order of x minus what? Don't say y.
Minus the order of x union y? Well, not union, intersect.
Intersection, right. And the order of y minus x is equal to what? The order of y
minus y intersect x.
Yeah. Oh. So the order of x symmetric difference is equal to the order of x plus the order of y, right? Minus what? Well, I'm sorry. It's the order of this plus the order of that, which is order x plus order y minus what? How many of these?
2. So minus 2 order of x
Yeah.
intersect y.
Yeah. Where this is what? That number right there is
Even.
even, right? Therefore, right, if the order of x is odd, then the order of x is equal to, right, an odd number plus the order of y minus an even number, which is even if and only if what?
The order of y is odd.
Yeah. Right. And if the order of x is even, then the order of x intersect y is even plus the order of y minus even, which is even if and only if what? Right? Even plus even is even. Plus the order of y remains even if and only if,
Y is even.
yeah, the order of y is even. So this equivalence relation on subsets, which was, a little kind of tricky to prove, was an equivalence relation, has what? Just simple equivalence classes, right? X is related to everything. When order of X is odd, it's related to every other subset whose order is also odd. And when the order of X is even, it's related to every other subset of even order. So the equivalence classes are just what?
For this situation, odd and even.
Yeah, just odd and even. So for, this relation, relation S, right, the equivalence classes are the set of all X that is a subset of A, such that order X is even, and the set of all X subset of A such that the order of X is odd. What should be the thing in the bracket here? Well, there's a lot of different choices you can make. Right, but what would be the obvious subset to choose that has even order that's always there? What would be the obvious even ordered subset to put here? Always
2x.
What's that?
2x.
Well, that's not a subset. You can't multiply sets by something. In general, anyway. Which subset of A
So 2.
has even order, and it's always a subset of A? So this isn't 100% right, what I put here. It's not 100% right. There's one counterexample to this. One set, which is a counterexample to this discussion of equivalence classes. One set.
Maybe the empty set?
Yeah, exactly. The empty set has no subsets of odd order. Every subset is of even order. Because every subset is just the empty set. Right? So, what subset of even order always exists for any set A?
The empty set?
What subset of even order always exists? In the power set of A. What's the first thing that you put for the power set of A? What's the first element that one puts?
The empty set.
Right. What's the order of the empty set?
0?
Yeah. Is that even? Is that even? 0?
Yes.
Yeah, of course. right? And then, well, I mean, as far as a subset of odd order actually existing, as long as A is non-empty, right? There's going to be some such thing. The equivalence classes are this as long as the set A is not equal to the empty set and has, some element little a in A. I mean, whatever little a might be. It could be a number, it could be a shape, it could be something. Depends on what the set A is. So any subset of order 1 has odd order, and the empty set is the only subset of order 0 that has even order. So yeah, that equivalence relation, it's interesting. In that, yeah, I mean, it's kind of hard to show it's an equivalence relation, but kind of, well, I mean, it's okay, it's reasonable to show that it's an equivalence relation, but the equivalence classes are just two of them, just the subsets of odd order and the subsets of even order. Has anyone taken, well, probably not yet. If you ever get the chance to take our class on error correcting codes, it uses this kind of structure. It's a pretty interesting class too. It's kind of geared towards engineering in a way, but it's got a lot of very interesting mathematics going on inside of it as well. I think it's 4260. It's cross-listed as a graduate course. It doesn't require this class that we're taking as a prerequisite, but it's a nice class if you ever do get a chance to take it. I don't normally teach it myself. I taught it once. Okay. So those are equivalence relations, but what about other types of relations, special types of relations, not just random relations? Partially ordered sets definition. So a relation less than or equal to on a, so we don't use twiddle anymore when you're talking about partially ordered sets. You always use this. Okay, on a set A is called a partial ordering when it satisfies the following three properties. It's reflexive. Reflexive. I always want to put an S there. Reflexive for all x in A. X is less than or equal to x. It's antisymmetric. Antisymmetric. So whereas equivalence relations are symmetric, partial orders totally not symmetric at all, ever. For all x and y in A, okay, x less than or equal to y and y less than or equal to x. So if that ever happens, it means x and y are equal. In other words, it's never symmetric. You never have a symmetry, right? I mean, unless the two things are equal, in which case, of course, you have a symmetry because x is less than or equal to x. X is less than or equal to x, so x is less than or equal to x. But I mean, that's not really symmetry. And then transitive. So I mean, it's the same as equivalence relations in a way. You just take away symmetry. Transitive for all x, y, and z in A, x less than or equal to y and y less than or equal to z implies x less than or equal to z. And that one has a special place in my heart. X less than or equal to y, y less than or equal to z implies x less than or equal to z. I won't go into why.
Just ask why.
When I was in school, my as high school guys always seem to do, talk about which team is the better team in whatever sport you're thinking about at the moment, and my one friend would always just sort of rank them for me with mine at the bottom, because he would always say, well, the Steelers beat the whoever, and whoever beat these guys that you like, so the Steelers are obviously better than those guys. So he would always say that, and then he would quote this. So,
On his part.
huh?
So well played on his part.
I'm sorry, I didn't hear you were cutting out.
Never mind.
Yeah.
Don't worry about it.
Yeah. So he would always like to taunt me because I was, I was always a hothead growing up. Still am. Anyway. So, for example, anyone care to give an example?
All integers.
Yeah, the set of all z under the usual, well, not just z, but the entirety of the real numbers.
Yeah. All
Under
real
the-
numbers, I guess, too.
Yeah, under the usual meaning of x less than or equal to y is a partially ordered set. In actuality, it's a total ordering, because every x and y, either one is x is less than y or y is less than x. So it's a partial order, but normally we say totally ordered set, because for every x and y and r, either x is less than or equal to y, or y is less than or equal to x. So it's not the best example of a partially ordered set, because it's a totally ordered set. What would be a partially ordered set that you've seen already?
So we're saying it's not partially ordered because x can never equal y.
X could equal y. Oh, I'm sorry. For every x and y and r, you have one or the other. X is less than y, or y is less than x. Well, with partially ordered sets, that doesn't have to be the case. Certain things can be incomparable. One is not less than the other. They're just unrelated.
So if you had like a list of numbers, let's say, and then threw in a shape, that would be partially ordered, as the shape would not be able to be compared to the numbers.
A what shape? An N shape, you're saying?
If I said like, so would like a list of numbers, let's say 0, 1, 3, 4, but then you throw in like a circle.
It's still totally ordered, right? It's still totally
The
ordered.
circle couldn't be compared to the others.
Oh, you mean like like that, like A, B, C, D? Something like that, you're saying?
No.
Okay.
I'm talking about having one of them not even be in there.
Oh, one of them not be a number. Well, let's do one with numbers. Think of this. Okay, any other orderings? Example, Z under the, not this relation. Under the something relation. Okay, not this, because that's going to be a total order. Where would you get a partial order? I mean, what sort of ordering on the integers? Let's say the positive integers. Forget about the negative ones for now. What sort of ordering on the integers do you have where, you've got reflexivity, you've got transitivity and antisymmetry, but you can't always compare integers. You have seen it. It's a weaker relation than less than or equal to. For example, like 4 is less than 7, right? So that's the less than or equal to relation. But 4 doesn't what to 7? 4 is less than 7, but what does 4 not do to 7? That it does do to 8. 4 is less than 8.
Evenly divide it?
It doesn't divide, yeah. So not division, the divisibility relation. All right, say that right, x divides y when x evenly divides y, and that is y is a multiple of x. Okay, is this reflexive? Right, well, for any integer x, well, does x divide x? Is x a multiple of x?
Yes.
Yeah. Antisymmetry. For every pair of integers, so for every pair, if x divides y, so if y is a multiple of x, and then x is a multiple of y, then must we have that x and y are actually the same? Well, think of it this way. If x divides y, must x be smaller than y?
Or equal to?
Yeah. If x divides y and y divides x, then x has to be less than or equal to y. Nothing bigger than y can divide it evenly. And if y divides x, then y has to be less than or equal to x. So, yeah, x equals y. And transitivity, right? So if x divides y and y divides z, right? So does x divide z? Well, x dividing y means y is a multiple of x. Then y is equal to k times x for some k. And z is a multiple of y. Z is equal to YL for some L. So Z is equal to, how does it do that? Ugh. Z is equal to YL, and then Y is equal to KXL, so that's equal to KLX. So Z is a multiple of X. That is, X divides Z as required. So the divisibility relation is a partial order, okay? And it's not a total order, right? So this relation on Z is a partial Z plus, is a partial order, but not a total ordering, right? For example, not every pair of positive integers is related at all, right? 4 does not divide 7, and 7 does not divide 4. 7 and 4 are completely unrelated. Another example of a partial order. It uses a symbol a lot like this one. A lot like that one, but not quite the same. Subsets. Yeah. Given a set A, the subset relation on power set of A is a partial ordering that is not a total ordering. Right, because sometimes some two sets are not comparable at all. They're not related at all. So, for example, A is equal to 1, 2, 3. X is equal to 1 and 2. And Y is equal to 1 and 3. Right? X is neither a subset of Y, nor is Y a subset of X. Okay, so a partial order that is not a total order. Can anyone think of other examples? let me leave you to think about that for next time. Okay, so now given a partially ordered set, less than or equal to on a set A, the Hasse diagram is well, one can think of it as a directed graph, or one can think of it as just a picture on a flat surface. So, is a depiction of the elements of A with a downward sloping line or path connecting X down to Y, well, X up to Y, if and only if X is less than or equal to Y. So, for example, let's take the set A, 1, 2, 3. Now, the subsets of A are, well, there's 8 of them. There's the empty set, right? 8, 2 to the third. There's the set containing just 1, set containing just 2, just 3, 1 and 2, 1 and 3, 2 and 3, and 1, 2, 3. A itself. So it looks like this, the Hasse diagram. For the subset relation on the power set of A is as follows. So at the bottom, you've got the empty set. And then the empty set, well, every set contains the empty set. But we don't want to connect every subset to the empty set because, you know, that would be too many lines. One could do that, but it's easier to do what I'm about to do. 1, 2, 2, 3, 1, 3. So 1, the set with 1 is contained in the sets with 1 and 2. And the set 2 is 1 and 2 and 1 and 3. The set 2 is contained in the set containing 2, 3, and 1, 2. And the set containing 3 is contained within the subsets 1, 3, and 2, 3. Make them like this. That doesn't look quite as good. Like that, and like that. And then all of those subsets of order 2 are contained in the entire set A itself. And there's a Hasse diagram for the power set of A, where A is just this set 1, 2, 3. Okay, so the empty set is contained in 1, and 1 is contained in 1, 3. So the empty set is contained in 1, 3, right? Because you have a line sloping upward from empty set to here to here. From empty set to here, right? A couple different ways you can get from the empty set to here. So the empty set is contained in 1, 3. And of course, everything is contained in 1, 2, 3, so you always have from every subset in the power set of A an upward sloping path from that subset to 1, 2, 3. Right? Like this, like that, so on and so forth. Let's look at that divisibility relation. Not on the entire set of integers, but maybe just what would be a good example? What's a number with lots of divisors? Oh, 60. Consider the integer 60, and 60 is equal to what as a product of prime numbers? As a product of prime numbers, what is 60?
2, 2, 3, 5.
2, 2, 3, 5, right? As a product of prime numbers. So, I mean, you'll cover this in the modern algebra class. Essentially, every integer is a product of primes, uniquely. I mean, you probably already know this. You may not have thought about it much, but I mean, every number is a product of primes because if it's not a prime, you just keep chopping it up until you get primes. Right? So you can get every number as a product of primes, and that product is unique, up to shuffling around the order, of course. And then one number is going to divide another number when the prime factors of the smaller number is contained within the prime factors of the bigger number. That's why 4, right, doesn't divide 7. 7 itself is just prime, so its prime factorization is just itself. Right? Well, this prime factorization doesn't fit in here. But like the prime factorization of 12, right, is this. Right? So 4 fits inside there. So 4 divides 12. So that's a nice way of looking at divisibility. So consider the integer 60 and all of its divisors. What are the divisors of 60? Well, it's all just, partial factorizations of 60, using these primes. So, I mean, you got 1, which has no primes in it at all. You got 2 by itself. All right, you've got 2 times 2. I mean, I'm not even going to write what that integer is at the moment. And then 2 times 3, 2 times 5. 2 times 2 times 3. Oops. 2 times 2 times 5. All right? And then, well, maybe I should just do, 1, 2, 2 times 2, 2 times 3, 2 times 5, 2, 2, 3, 2, 2, 5. And anything else with 2? 2, 2, 3, 5, the whole thing itself, 60. Oh, and then 2, 3, 5. What else? Things without 2, just 3 by itself, just 5 by itself, and 3 times 5. I think I got them all. Did we get them all?
Yeah, you got them all.
I don't know. We'll find out. Here is the Hasse diagram for the divisibility relation. On the set of 60 and its divisors. Well, at the bottom, there's going to be the 1. Well, at the top, there's going to be 60. We'll go top down, right? Which is 2 times 2 times 3 times 5. Now, 60 is going to be divided by And how many of the primes we've got here? 4. If we want to go down one level, right, we're just going to get instead of using all 4 primes, let's use just 3 of them. How many different ways is that going to happen in 4? 2 times 3 times 5. 2 times 2 times 5. Or is it just 3?
I think it's just 3 because the 2 is repeated.
Yeah, it's because you're always going to have a 2. Yeah, there's only 3 of them. So 2 times 2 times 3, which is 12. 2 times 2 times 5, which is 20. And 2 times 3 times 5, which is 30. Now, if we're just going to use like 2 of those 4 primes, well, we can take away 1 from here, which would give me 2 times 2. Or 2 times 3, which is 6. Here, well, you've got 4. 4 goes into 20. And you also have underneath this one 2 times 5, which is 10. Here, well, what's the only one out of these that we're missing so far? We've got 6, we've got 10. Well, we don't have 15. And then 2 times 5 goes here. 2 times 3 goes here. 4 does not. So 2, 3, 2, 3, 2, 2, 2, 2, 2, 5, 2, 5, 3, 5. Anything else? 2, 3, 5. 3, 5, 2, 5, 2, 3, 2, 2. And then just 1 at a time. 2, 3, 5. 2 goes here, here, here. 3 goes here, and here. 5 goes here, and here. And then 1 on the bottom. Right, so this diagram shows, this Hasse diagram, it shows all of the divisibility relations. Right, so 3 divides 15, it divides 30, and it divides 60. Right, just go upward from 3. 3 divides 6, divides 12, it also divides 30 going this way, and it also divides 60 going this way. But, like 20 and 3, there's no path going from 20 down to 3. Nor is there, a path going up from 3 to 20. 3 and 20, they're incomparable, right? There's no path. No path from 3 to 20. But there is a path from 3 to 12. There is a path from 2 to 30, from here to here. But there is no path from 2 to 15. 2 doesn't divide 15, right? So this Hasse diagram, it depicts very neatly all of the divisibility relations between the integers within 60 and its set of divisors. So this is one reason why I think, at least it's not for sure, certainly not an expert in it. It's one of the reasons why the number 60 has kind of a lot of historical importance. Why a circle has 360 degrees, which is totally an artificial choice of number, but it's a nice number because it's got a lot of divisors, as does 60. Right? Babylonian sort of base 60 number system, and 60 is nice because it's got a lot of divisors. Because this prime factorization has a lot of primes in it, and yet the number isn't too huge. Makes a little sense to me, anyway. Okay, so that's the lecture for this chapter. So again, the homework assignment for chapter 5 here is going to be due on Wednesday next week rather than Monday. So next time we meet, let's take some questions on the homework assignment, and we'll do maybe one more enrichment topic and then go on to the next chapter and talk about what the second exam is going to be covering. Okay? All right, everybody. Have a good afternoon, and email me if any